All right, today we're putting on our engineering hats. Our mission? To crack open the black box of a matrix transformation, figure out how it ticks, and then build the one thing that can undo it all, its inverse. Okay, let's get in there and reverse engineer this thing.
So, what's the whole point of this? Well, it's all about hitting the undo button. Imagine a matrix, let's call it A, takes a perfect, normal cube and just twists it, stretches it, and turns it into something totally different. The inverse, A inverse, is that one-of-a-kind matrix that can grab that twisted shape and snap it right back into that perfect original cube, what we call the identity state. It's the ultimate reset switch for transformations in space. But hang on, before we even start drawing up blueprints for this reversal machine, we have to run a super important diagnostic. I like to call it the gatekeeper test. It asks one and only one question. Is the determinant of our matrix 0? If the answer is yes, the matrix is what we call singular. That means the transformation has squashed space down in some way, making it irreversible. The gate is closed, process terminated. But if the determinant is anything other than 0, the matrix is non-singular. The gate swings wide open, and we're clear to proceed. And here's that test in action. Look at matrix B on the left. You do the math, and its determinant comes out to 0. That's our red flag. It's a singular matrix, so we can't build an inverse. Full stop. Now look at matrix A on the right. Its determinant is -10. That's not 0, so we get the green light. It's non-singular, and we are good to go. You see how this simple check can save us a whole lot of wasted effort? Okay, so we've passed the gatekeeper test. What's our game plan? Well, that really depends on the machine we're working with. If we've got a simple 2x2 matrix, we have a lightning-fast, one-step engine. But for a more complicated 3x3 matrix, we need a whole 5-step assembly line. You see, as matrices get bigger, the way all the numbers interact gets way more complex. So a simple little shortcut just won't cut it. We need a system. Let's start with the simple 2x2 model to nail down the basics. The 2x2 engine is just beautiful. It's so elegant. It's basically a two-part move. You swap the two numbers on the main diagonal, and you just flip the signs on the two numbers on the other diagonal. Then, the only other thing you do is scale the entire matrix by 1 over its determinant. That's it. Swap, negate, scale. It's so quick it almost feels like you're cheating. Let's run a quick example through the machine. Step 1, the gatekeeper test. The determinant is 1, not 0, so we're good. Step 2, swap and negate. The 7 and the 1 swap places, and the 3 and 2 become negative. Easy. Step 3, scale. We multiply by 1 over the determinant, which is just 1, so the matrix doesn't even change. And there you have it, the final product, our inverse matrix, assembled in just a few seconds. All right, time to level up. Welcome to the 3x3 engine. Now this is not just a quick formula, this is a full-blown 5-step assembly line. We'll take our main subject, matrix A, and guide it through 5 crucial phases. First, we calculate the determinant, then we find the minors, apply the cofactors, create the adjoint, and finally, we put it all together with the formula. First up on the line, phase 1, extracting the determinant. This gives us what I like to call our scalar component. It's just one number, but it represents the entire scaling factor of our transformation. For our matrix A, we run the numbers and we get -1. Perfect. We're just going to set that value on a shelf for now. We're going to need it for the final assembly at the very end. Okay, on to phase 2, the minor extractor. This is where we start building the main body of our inverse, what I call the grid component. Here's how it works. For every single number in our matrix, we do a little bit of surgery. We cover up its entire row and its entire column. And what's left behind? A little 2x2 grid. We just find the determinant of that tiny grid. That number is the minor for the original position. So, after we run that extraction process on all 9 positions, one by one, this is what we get, the matrix of minors. You can see the basic structure is there now. The architecture is built, but it's not quite ready yet. The mathematical signs are kind of out of phase. It still needs a little calibration before we can move it down the line. And phase 3 is exactly that calibration step. We bring in a special tool called the cofactor mask. Really, it's just a simple checkerboard pattern of plus and minus signs that we lay right on top of our matrix of minors. The rule couldn't be simpler. If a number is sitting under a minus sign, you flip its sign. If it's under a plus sign, you leave it completely alone. And here's that mask in action. We take our uncalibrated matrix of minors, apply the sign mask, and out pops the cofactor matrix. See? The necessary signs have been flipped. The grid is now perfectly calibrated and ready for the next station. We are so close now. Phase 4 is a final mechanical tweak called the transpose.
The best way to think about this is like a hinge. We lock the main diagonal, the line from the top left to the bottom right, we lock that in place. Then we literally just fold the matrix over that hinge so the numbers on either side swap places. And the result of that fold? We get the adjoint matrix. This is it. Our grid component is now officially finished and secured. So let's take stock. We've got our scalar component, the determinant from phase 1. And now we've got our grid component, the adjoint matrix, from phase 4. We are finally ready for assembly.
It's time! Phase 5, the final assembly. This is where we bring our two finished components together. And the formula is beautifully simple. The inverse is just 1 over the determinant, that's our scalar component, multiplied by the adjoint matrix, our grid component. You can see all the parts finally coming together.
So all that's left is to actually multiply that scalar through. Remember our determinant was -1? Well, 1 over -1 is just -1. So we multiply everything inside our adjoint matrix by -1, which just flips every single sign. And there it is, the reversed machine. The inversion is complete. This matrix right here will perfectly undo any transformation made by our original matrix A. So there you have it. We've taken the whole process apart and built an inverse from the ground up. And now the blueprint is yours. Here's a brand new system for you to tackle. You've got the 5-step checklist: get the scalar, extract the minors, apply the mask, do the transpose, and assemble it all. Run this matrix through the engine and see what you come up with. What we've really done today is shown that finding an inverse isn't just about crunching numbers. It's about systematically engineering a tool that lets you go backwards. And that skill is absolutely fundamental in everything from 3D graphics and robotics to cryptography. Which really just leaves us with one last question to think about. Now that you know how to reverse the machine, what are you going to build with it?